I think that works for
Yes, I can give you your results.
Yeah.
I'm on my laptop actually, I can use you at the end. I'm sorry, is this? It is on. Okay. Now, just before we start, there's something I have to correct. Something I said incorrectly in the lab. I think I told you about this towel, yes, in the class yesterday, but I didn't tell you. Do you remember in the Excel lab I did all the calculations, and then at the second last thing I did was uncertainty of y divided by uncertainty of x. Yes, and then the last thing I did was the ratio divided by n. Remember that? So the very last thing I did was divide by n. That's a mistake. It's divide by square root n. Okay? So on your Excel file, you'll need to change that to square root n. Okay? It's not actually n. And the reason for that is you'll learn it when you do statistics at university. But whenever you have a really big sample of data, the error is inversely proportional to the square root of n, not n. Okay? So it means that you need a really, really big sample to make the error really, really small, because you have a square root n instead of an n. So if you want, like, you know, a 1% error, then you would need, let's see, square root 1% would be square root of 100. I think you would need something like, hang on. Yeah, you would need 10,000 points to have a 1% error. Now, wait, now that is only true when we're talking about sampling, like, people for surveys and questionnaires. It's not as much for when you need physics, because remember, in our formula we have uncertainty of y divides uncertainty of x over square root of n. So because of that numerator, it means it's not as bad as needing 10,000 points. But if you have something completely random like surveys, this is why, you know, surveys are so big. You need 10,000 people before you can get a good value. Okay, so just remember square root n at the end, not n. Okay, so we'll continue. What? How much do those cost you? Let me show you something. No, seriously, I bought this last week. Let me show you. Look at this, right? Look at this. This is Bluetooth, so I can use it with my laptop. 10-meter range, so I can walk anywhere in the house, right? And it's pretty good.
Safe.
How much do you think this cost me? Including postage from Hong Kong. Less? Less? Less?
5 euros.
Little more. 12 euros, including postage, from Hong Kong.
Well, this is a mixer, like, I can hit it with the sound at the same time. Why?
You're not selling it to me. You're not. So how much do beats cost? Alright, so let me just put them side by side. What do you think? Which would you pick? I'd pick the 12 and keep the 178 euros. Or buy 10 of them, yeah. Because even if this only lasts me 1 year and then it breaks, I still think that's good. Alright. Now, have you done the ideal gas law in chemistry? Oh, you haven't?
We have, yeah.
So what is the ideal gas law in chemistry? What is it? Yep. PV equals N or T. Now what is the N? No, I don't think it's that bad. Do you need it all?
No, it's okay.
It's okay. What's the N for? Moles. This is the number of moles.
Did
Now,
you do it last time?
oh yeah, I did the proof for the formula, didn't I? And if you don't want to use moles, if you want to use instead number of particles, what's it called? Molecular compounds, isn't it? What we could do then is use PV equals N. But then we have a different constant here. Yeah, KB is the name of the constant T. And we actually saw this constant last time as well. It's Boltzmann's constant. And it's pretty much the same as ideal gas law constant, except we divide by Avogadro's number, wasn't
Why
it?
do you call it KB instead? Why not just K? Mole?
Some people just call it K. But I think it's because K is so general. Just K is fine. I don't know what I think it might be KB in your formula book. In fact, I think on the calculator it's just K. Yeah?
Can we use, if we want to keep R, can we do more maximum R?
Yes, yeah. But I mean, the way these work in the exam is every question I've seen requires the first formula. So let's have a look at some examples.
So they don't ask for a second one.
They don't have to what?
So they do not ask for a second one.
No, but it's in the syllabus. The syllabus says students should be able to use that and that, and they have never done the second one in the exam, but it's on the syllabus, so I'll show it to you. Any other questions? No. Okay, let's have a look at some examples. So the first thing actually I should say is the name of this formula is the ideal gas law. Now, can we always use this formula? Well, no, not always. Most situations we can. Yeah.
The word is medium.
The word?
But the 4 pictures is medium.
For the 4 pictures? Well, it was medium.
Yeah.
Medium size, medium rare. But what was the man? Medium build?
Medium between the spiritual one and like a...
No, that would never have happened. And what was the other picture? There was...
Media, yeah. Like a lot one.
That's terrible. No, you don't want to know. You really don't want to know. Okay, so we can't always use the ideal gas law. There's some assumptions we need to make about our gas, or that we need to have true criteria before we can use the formula. So the first one, okay, the particles, well, no, I don't say the parts, and by parts I could mean atoms, if they're atoms, like for example H2, or molecules, if they're molecules, molecules, etc. Whatever it is, H2, molecules, I don't know. Water isn't a gas anyways, but you know what I mean by a molecule, like H2O. The parts must have no interaction term. Now what does that mean, no interaction term? Well, I'll give you an example which you would be familiar with from chemistry. You know, with a proton and an electron, one is a positive charge and the other is a negative charge. So what would happen if they were nearby? They'd attract each other. That's what I mean by interaction. So, for us to use this law, there must be no interaction term between the parts, the particles, the elements, the molecules. They must be kind of independent objects just moving around in space.
For example?
Just like helium. You know, helium doesn't interact with other helium elements. It just fills up the space. Whereas, if I had some, some other helium with...
What about H2O in water? I mean,
Yeah, well, a H2O maybe is a better example of when you can't use it. because there is a bit of interaction between them, isn't it? Like you can kind of...
Hydrogen bond?
Well, between the hydrogen and the oxygen.
That's why the drop stays together. No, but you said that there's no interaction between atoms or molecules. So
No. This is in brackets. No. This is in brackets. What I mean by part, I mean whatever the thing is that's making up the gas. So here it's like H2, whereas if it was water, it's H2O. But in the case of H2O, I think you get a bit of interaction between the H2O molecules. So in other words, H2O in liquid form, you know, it's not a gas, of course. It doesn't just fill up the space. That there's an interaction between them. Now H2O in steam, vapor form, then that's probably okay because it doesn't really interact. You know, you don't really have blobs of H2O steam. You know, it'll still spread out. I guess what I'm trying to say for the first assumption is the particles need to behave as if they're independent.
Will they be mentioned in the question?
Oh yes, I've seen questions as asked before. Give 3 assumptions required for the ideal gas law. So there are many assumptions. The first one is that the particles are independent, that they do not interact. Yes? Okay. And when they collide, there is no loss in kinetic energy. So the other thing is when your particles collide, there's no loss in kinetic energy. And what's this called from mechanics when you don't lose kinetic energy in a collision? No, perfectly elastic. So the second assumption is that they're perfectly elastic.
Is that possible?
Well, this is the thing, I mean, practically so, but it can never be perfectly so. But I mean, you know, if you have, for example, Joshua, 99.99% of the kinetic energy remaining, then that's close enough. You know, I won't be able to get 100. Because when they collide, I don't know, you might knock an electron or something. You know. Okay, so that's the second assumption. So if we think back to the proof I did yesterday, any other assumptions that we had that you can think of in my diagram about the movement?
How about the velocity?
Yeah, what about the velocity? What could we say about it?
It remains constant.
Good, yes, okay, good, yeah. That the velocity, that the average velocity is a constant, that your gas, it's not doing some weird thing with its velocity where all the particles are suddenly getting faster and faster. Okay? Well, I think that's a little bit too unclear maybe. I think we can do something else. The velocity is a good idea. Yeah, what about the container? Yes. A little bit too weak, but still a good idea.
Average velocity is proportional to the velocity in one vector.
No, it's getting a bit tricky now, isn't it? I would say the other thing, I don't think it was really so clear. It wasn't so clear in the proof, the formula, but in fact, you need PV to be pretty small for ideal gas law. It doesn't work so well if PV is very big.
How small?
No, well, not really, because it depends how accurate you want your calculations to be. I'll just tell you this, that we have PV equals N or, well, small n, N or T, yeah? In fact, that's the ideal gas law, and it works very well for most gases which are ideal, meaning that, you know, there's kind of a low pressure, low volume, the collisions are nice, but of course not all gases are like this. when you go on to university, you will learn that you can improve this formula by adding an extra term in, which I think would be something like some constant multiplied with temperature squared.
Why would they?
Why what?
I mean, why would they add it?
Oh, because, well, maybe it's a little bit of an English thing here. What does the word ideal mean?
Perfect.
Yeah, it means kind of a perfect situation, which is the particles collide, they don't lose kinetic energy, everything is nice and clean. But realistically, it's not like this. Some particles will stick together. When particles collide, some of them will lose kinetic energy. You know, if you think about a liquid like water, if I stir the water and give it a velocity, and the particles are collided, will they lose kinetic energy or will they keep colliding at the same velocity? No, they'll lose it. And you see this because you stir the water and then it slowly comes to rest. So there's kind of an internal friction, an internal loss of energy. So this formula is no good for water because of this. Assumption is not true. What I'm just saying is, at university, you will see improved formulas that have extra terms in it. So I think the next term in the formula, they would add in a t squared term. Okay? So that's all I'm saying. That's all I'm saying here. That usually PV is a small number. I'd like to say, what exactly is small? You don't have to worry about that because for all the questions they give you, it will be considered small. Okay? Now, PV equals N or T. So another way of saying it, I guess, is that the temperature is pretty small as well. And again, what does pretty small mean? Well, I suppose, not more than about 300 Kelvin. No.
Or the temperature is equal to number of
Oh yeah, you can look at other ways around like this. Or, if you have way too many moles, if the mole number is really big as well. But anyway, roughly speaking, we just say that PV is small. Okay. Any other assumptions we can write them as, you could also say things like that the density is pretty small, which it needs to be anyways because it's a gas. You don't want some really heavy gas that's like a solid that just falls to the ground.
Temperature.
Again, temperature, you don't want that to be too big, I suppose you could say, to use the ideal gas law, you probably want the temperature not too big, not too small. Well, you want it above zero anyways. I'd say about, really you don't want to be going too much past 325 Kelvin. Okay, let's have a look at some examples. Can I scroll down? Yep, okay, so let's have a look at some examples. Right, okay. So we have a tank, and let me give you the radius here. I don't know, we'll say the radius is 0.5 meter and then the height is 1 meter. And we put it in, we put a gas inside here, and we'll put out a temperature of 20.4 Celsius. And we'll say that the pressure in the tank is 2 times 10 to the 5 pascals. Here, let's just make our numbers a little bit easier. Let's make this what is it for converting? 273, isn't it?
Yeah, 27.
So yeah, we'll make it a nice 27 then, Celsius. Okay, so I'd say first question then is, what's the volume? Now what do we know? We have pressure, temperature. Oh yeah, I should tell you the number of moles in it as well. Let's see, PV equals N or T. We know the P, we know the V, we know the T. Oh yeah, okay, so I'll ask you for the volume first, and then I'll ask you for the number of moles. We'll do this first. Get started. Okay, so how can I get the volume? Well, because I have the shape, it's just pi r squared h. Can someone hit that in on the calculator for me? Tell me what you get. 0.785 meters cubed. Okay, now we want the mole number of moles, so we have PV equals N or T. So we have N equals PV over RT. Now the pressure is 2 times 10 to the 5. The volume is 0.785. The ideal gas law constant is 8.31, and the temperature in Kelvin, and it must be in Kelvin, is 300. So what's that, please, for the N?
Can we convert the constant to from Kelvin to Celsius and then to Celsius?
No, I don't recommend this. I recommend always make
No,
it.
but we can, right?
Is possible, but let's use Kelvin.
Yeah,
Yeah.
that's it. That's so I'm just asking, can we?
Yeah. Yeah. 62.97.
98 actually.
All right, we'll just say 98 moles. Okay, now the next question. So that was part 1, that was part 2. So we have the volume, no problem. We have the mole number, no problem. Next, I want the density of the gas. Now wait, before you start this, what's the formula for density? Mass over volume. Do you know the volume? Yeah. Do you know the mass? No. How could you get the mass?
From the moles.
No.
Oh yeah, from the moles.
The moles. So what do you need to know? You need to know the molar mass, the mass of 1 mole. So I haven't told you this yet. All I tell you is that the gas is H2. This is the gas. So I'll tell you that the gas inside here is H2. Now tell me the density of the gas. So you'll need to use some of your excellent chemistry knowledge. Did you write this down? Yep, okay. What did you get?
Yes, sure. 160.4.
160.4. What's the unit now for density?
kg.
What did you get? 160.4.
160.4.
That seems kind of large.
8.23.
No, I know what mistake you've made.
You get 160.
Yes. What did you guess?
0.1604.
Yeah, what did you guess? Alright, here.
I give the volume.
Okay, we all have different answers. Right, so let's have a look at it.
It's almost the same, just a
It's almost
different
the same, I
decimal.
didn't know of the volume.
Oh, the volume is the problem.
Yeah, I calculate it, I didn't use the 0.75.
Oh, okay. Let's have a look here. So how many moles do we have? We have about 63 moles of H2. What is the molar mass of H2? 2, roughly 2. So this means 1 mole of H2 is 2 grams. So 62 moles, about 126, about 126 grams is the mass. So the density is the mass over the volume, which would be, it's roughly about 2.0002, something like this for H2, multiply 62.98. Now don't forget this is in grams, so we have to do a 10 to the minus 3. All over, and what's my volume? 0.785. Okay. What do you get if you type that in exactly, please?
0.16.
16, give me one more.
0.
Okay, alright. Kilograms per meter cubed.
1 minus 3.
Because it's grams, molar mass is in grams, and we use kilograms per meter cubed as our volume.
Can we give an answer in grams?
Yes, you can give your answer in grams per centimeter cubed, no problem. Yes, we're dying.
Why do you use 10 to the power of minus 3 as the denominator?
kg.
Tal, what did you ask me 20 seconds ago? What was your exact question 20 seconds ago?
Can we use grams? Oh yeah.
Do you do this just to, like, punish, to see how much you can push your teacher? And yes, Hamish, before you ask me, you can use grams per centimetre cubed if you want. Okay. Dang. Alright. So now the next question, so I'm going to keep building on this example to get all the ideas in place. So the next thing now is the tank is opened until the gas is released. Okay. So my next question is, how many moles of H2 leave the tank? Okay, so
pressure is 10.5.
yes, this is the thing now. How can we do this? How many moles leave the tank? So what I do is I open the tank and I let the H2 out. So then what's my new information, or what has changed? Firstly, has the volume of the tank changed? No. Has the pressure changed? Yes, definitely. The N? Yes. The or? No. And we'll say the temperature is the same. Okay? So two things are different, the pressure and the volume. The pressure and the N. But one of those things you know. Pressure is what? It's the atmospheric pressure, isn't it? Which I think we said is 1.01 times 10 to the 5. So you can just say, for that day, it was just 10 to the 5. Okay, 10 to the 5. So I want you to tell me how many moles of H2 leave.
What's the temperature? 20.
It's the same temperature, 27 Celsius.
Almost everything.
Almost everything, really.
60%. 62.9.
No, that's not almost everything, just a whole lot of it, yeah.
No,
I thought you were going to say something like 63.97.
0.01 was the same.
0.01? That's okay, that's something. And that's how much left, is it? That's how much we'll say, 0.01 only? Oh, there.
I got 31.4.
I got 31.5.
Okay, we'll do it now, we'll do it. So, look, PV equals N or T, so N equals PV over RT. In this case, the P is 10 to the 5, the V is still 0.7854, the R is 8.31, and the T is 300. So what does this equal?
31.49.
Now this is how much is in the tank though, so then the amount that left is equal to 63 whatever minus this, so what's that number? 21.4. Sorry, say that again here, right? 31.48. Okay, so that's half left. So then my next question, is what is the mass that's left? Well, that's kind of easy, isn't it? Because you could actually have a few ways you could do it. You could do mass as density by volume, but you don't know the volume. You could also do it as proportions, because you know half the H2 left, roughly. So about half the mass is gone. And what we worked out the mass previously, didn't we?
Yeah.
What was it? 125. So it's about half of that number. So if you wanted, you could do it as a proportion actually. The mass would be 31.48 over 31.48 plus 31.49 times previous answer of, do we have the, oh, we worked it out in the numerator here. Yeah. What did you say the number was? 1? Well, mass is density by volume anyway, so 0.7854.
Then we just use mass equals and
Yeah, I could use that one as well. Like I said, there's many ways to do it. This is one by using proportions. What was the density? 0.16, isn't it? Okay, that's one way of doing it.
Aren't you going to multiply 31.48 by 10 minus 2?
This is moles. Yeah, sorry, and then the other way, what was the other way you said? You could say mass is...
mass is n times molar
n times molar mass. So that's the other way of doing it, which in this case is 31.48 times 2.0002 or something, times 10 to the minus 3. That's another way to do it. In fact, there are many ways to do it. So what answer do you get?
62.984
62.984
grams. That's
kilograms or grams? 62.
62.984.
Yeah. And this is in grams. So it's quite small. Well, still about half of it. Okay, so I'll give you one more question for this one to do. Okay, so now we've let some of the gas out. So we've sealed the tank back up, okay? So we've closed the tank now. Okay, so I've closed the tank. So my last question for this one is, now I'm going to heat the tank. I want to heat the tank to a new temperature so that the pressure is back to the same value it was at the start. Okay, so my question is, what temperature do I need to heat the tank to so that it will be at the same pressure it was at the beginning? Because maybe I'm pretending I bought some helium gas, I steal some of it, and then I heat the tank back up so it looks like it's the same pressure. Not that you should do this, but tell me the temperature I would need to do this. You understand? No?
Yeah.
Yes? Okay. So, give me the key.
After the gas is left.
Yeah, after the gas is left.
Do you want to change the temperature or just the current temperature?
You can give me either. You can just give me the temperature if you want. 31.49. Okay, so what do we have there?
Just that.
599.9.
Oh yeah, it won't be just double it because of the proportional relationship. What is it?
599.9.
Yeah. I don't really think you'd get that in an exam because that temperature is too big. But anyways, if you let, it shows you the proportional relationship that if you let half the gas out and you want to keep the pressure the same, then you'll have to double the temperature to double the pressure back to the original value. Yeah.
But the amount of moles that left was 31.8.
No, not less. What you want is how many is in the tank. 31.49 is what's in the tank, wasn't it?
Yeah.
Yeah.
But 31.48 is what left.
Yeah.
So we are refilling to the original value.
No.
There's pressure though.
Where pressure we are returning to the original value. That gas is gone. We have the new value of moles inside the tank. You can't change that.
Can you give it the box?
No. Please, we are all friends here. Okay. So I'll give you some questions to try for a few minutes, but as you can see, what am I doing? I'm just using the same formula over and over again. So I really like this question in the exam. It's a nice, easy, straightforward question. It also relates to your chemistry, so it's something that you can do, and get full marks in.
Do we always get it in part B?
No, now here's the thing. Sometimes it's in A, sometimes it's in B. You should be really happy if you see this in part B. I mean, if you get a section B question on ideal gas law and materials, consider it a gift, okay, because it's such a good question to do. This does not always happen, Tal, but it is pretty common to get this in section A as a short question. Okay, Chloe? Yep.
What questions are they to choose from?
3 from 6. Yeah. Okay.
Just 3 after that.
Yeah. We did mechanics, electricity, and waves. So now today, actually this is the last materials lesson. Okay? So we have everything. No, sorry, that's not true. We have one thing left to do in materials, but I'll do that later in the course, which is to do with resistivity and resistance in wires. Again, it's not so difficult. Okay, can you try these for a couple of minutes? In fact, you might even get a lot of them done because they're so short. And then in the next class, I'll do the answers at the start, and then after I do the answers, we can have a look at the lab tray.
Can I take one for them?
Yes.
I'd like to hear it.